So here we go. The first problem says the element bromine has an average atomic mass of 79.904 atomic mass units and consists of two naturally occurring isotopes, bromine 79 and bromine 81. Given that bromine 81 makes up 49.31% of all bromine and has a mass of 80.9163 atomic mass units, calculate the percent abundance of the bromine 79. So that's what you want to zero in on. So we're given a lot of information, a lot of numbers, but let's just take a big picture and step back about what we're actually given. We are told that the average atomic mass of bromine, of all the isotopes, the weighted average is actually 79.904. So whereas in the last problems, that's what we were trying to calculate, the average atomic mass, in this problem, that is given to you. And then you're told the mass and the percent abundance of one of the isotopes, and then what we're trying to figure out is the percent abundance and the mass of the other one. So before we do anything else, let's write everything down, including the actual isotopes we have, because if you don't write things down, then you don't often know where to go. All right, so what we know is that the average atomic mass is the weighted average of all the isotopes is actually 79.904 atomic mass units. All right, so this is like the aggregate average of all the isotopes of bromine. But then we're told that there's two naturally occurring isotopes. One of them is bromine 79, that's a mass number of 79, and one of them is bromine 81. That's a heavier version with extra neutrons. How many extra neutrons? Well, 2 extra neutrons. You can see that the mass number is 2 higher. So this is a heavier version of bromine. All right, but we're also told that these are the two isotopes, and we're given that bromine 81 makes up 49.31% of all bromine, and it has a mass of 80.9163 atomic mass units. Now what we want to find is we want to figure out what is the percent abundance of this version of bromine, and we also want to find out what is the mass of this isotope of bromine. So this is what we're given, and when you write it down like this, it's, in my opinion, I mean, everything is open to an opinion, okay? In my opinion, it's much cleaner and easier when you have it written down like this than it is to read the problem over and over again and try to pull the numbers out. Because it's hard, does this number go with this isotope, this one goes with this one? But here, you can much more easily see that there's only 2 isotopes, and you're told the percent abundance of one of them. So the first thing says, calculate the percent abundance of bromine 79 and its mass. But it's very easy to figure out the percentage because we know that all of the isotopes in nature have to add up to 100%, right? So the percent abundance, so the percent of abundance of bromine 79, right? How do we figure that out? All we do is we take 100 and we subtract the percentage of the other isotope, 49.31. And so what we figure out is that when we take 100 minus 49.31, we get 50.69% abundance. And that's for bromine 79, right? And so this is the final answer. So you see how it's so easy once you write it down. You know, you may not know exactly how to proceed, but once you write it down, you realize there's only 2 isotopes and they have to add up to 100%. So the first part of figuring out the percent abundance is just very easy to figure out. All right, now the second part, what is the mass of that thing? Now this one is where it gets a little bit harder because we never asked you to calculate the mass of each individual isotope. We were solving problems before where we try to find the total, the average atomic mass of all the isotopes, but here we're not asking that. I'm asking you, tell me what the mass of this specific flavor, this specific isotope, what is its mass? This one has a mass of this one has a mass of this. So you may not know how to proceed in the beginning until you realize you can apply the same exact equation. The average atomic mass is given to us. This is the weighted average of all the isotopes, so we put that on the left-hand side of the equal sign, 79.904. This is what you're going to read on the periodic table. In fact, let's just go over to bromine real quick. 79.90. We just don't have the extra decimal there. 79.90. That is what's on the periodic table. This is the weighted average of all the isotopes for the average atomic mass. But this has to be the weighted average of the other isotopes. So we have the heavier isotope. This is its mass, 80.91. So 80.9163 multiplied by its fractional abundance. We have to slide the decimal 2 points back. So 0.4 0.4931, right? And then we have to add to that. Let me see if I can kind of squeeze it in over here, actually. We have to add to that the fractional abundance of, or the mass of what we're trying to solve for. So I'm just going to call it mass. And I know that what I'm trying to figure out is it's the mass of this isotope, of the bromine 79, multiplied by its percent abundance. And look at this, we calculated the percent abundance of bromine 79 in the beginning. And so we write it down as 0.5069 because we have to convert everything to decimal. So here is an equation, and we only have one unknown. And so you have to use algebra to solve it. So, you know, a lot of students say in algebra, why am I learning this stuff? Who cares? Well, this is a great example. When you're not given the information to go one direction in a problem, often you put the information you have in and you use algebra to backwards solve for what you're trying to find. All right, so let's proceed by just multiplying what's on the right-hand side. On the left, we still have the 79.904. And on the right, when we take 80.9163 and we multiply by 0.4931, what we get is 39.90. And then plus the mass of the other bromine isotope here, and then multiply by 0.5069. So how do we solve for m there? There's lots of ways, you know, that you can organize your work, but what we're going to do is, firstly, we're going to subtract this to get it away on the other side. We're going to have 79.904, and then we're going to subtract this number, 39.90. We subtract from both sides. On the right-hand side, it disappears, and on the left-hand side here, it shows up. And then we still have the mass times 0.5069. How do we solve for m? We divide both sides of this equation by the number here. And when we flip everything around on the other side of the equal sign, what we're going to get is 79.904, subtracting 39.90, and then all of that stuff is divided by this, 0.5069. So what we get is 79.94 minus 39.90 divided by 0.5069. Now, when we subtract on the top 79.904 minus this, we get 40.004. On the bottom, we're still dividing by this, 0.5069. And so the mass is going to be equal to, when you take 40.004 and you divide by this, you get 78.92. 78.92. This is atomic mass units. And what are we talking about? This is the isotope of bromine, 79. That's what we actually found here. Sorry, that's a little hard to read. Let me take the numbers away. Bromine 79, right? Because that was the one with the unknown mass. So yeah, you could put this this label here in the equation, but really just label it M, solve for what the mass is, and you remember what it was you're solving for, which is the mass of this isotope of bromine, 78.92. So basically what you figured out is that the only way that you can arrive at an average atomic mass of this, when one of the isotopes has this mass with this percentage, and the other isotope has this percentage, the only mass that works is the mass of 78.92 atomic mass units. When you put it into this equation and multiply and add, this is the average atomic mass you get, which we have already actually verified on the periodic table is the atomic mass, the average atomic mass of bromine. So basically it's going backwards. So sometimes you have to use a little algebra, but it wasn't like super hard. Certainly was not a super difficult equation to solve. If that equation looks very difficult to you, then I actually recommend that you go back to algebra and get a little practice, at least with some very basic equations, so that you feel comfortable with moving things around an equation. All right, now this last one requires us to use a little more algebra actually to solve, and here is how the problem goes. Chlorine 35 and chlorine 37s, which have isotopic masses of 34.9689 and 36.9659 atomic mass units respectively, are the two naturally occurring isotopes of chlorine. Calculate the percent abundance of each isotope based on the fact that the average atomic mass of chlorine is 35.4527 atomic mass units. So here, again, we have to go backwards. We're given the average atomic mass of chlorine, 35.4527. And I give you that there's two isotopes, and I give you their masses, and I want you to tell me what are the percent abundances of the two isotopes that must be occurring in nature to give me that average atomic mass. So even though, again, it doesn't look like we know how to do it, you have to just apply the same definition and use some algebra in order to get to the answer. So first, let's write down what we know. That's always the most important first step. All right. Now what we know is that we have chlorine, an isotope of chlorine called chlorine-35. And we also have another isotope of chlorine called chlorine-37. You see one of them's heavier than the other because here we have 2 extra neutrons. The mass number went up by 2. All chlorine has 17 protons in the nucleus, including these chlorines, but they have differing number of neutrons, and so that's why we see that up in the mass number there. Now let's write down their masses. We are told that this one right here has a mass let's see, what is it, 34.9689 AMU. And this one right here has a mass of 36.9659 atomic mass units. I really encourage you to write things down. Please write them down, write everything you know, right? And then the other thing you're given is you know the average atomic mass, the average atomic mass, which is the weighted average of all of the masses of the isotopes and their abundances, and that is given to us as 35.4527 atomic mass units. Now let's just double check, just for giggles. 35.45 for chlorine, 35.45 is the weighted average of the atomic mass of all the isotopes of chlorine. So that's what we see on the periodic table. So this makes sense. Now what are we actually trying to figure out? We're trying to figure out the percent abundance of these 2 individual isotopes. Are they 50-50? Almost never do you have equal splitting like that, right? But one of them is probably going to be a higher abundance than the other. Which one is more abundant than the other? The problem actually says calculate the percent abundance for each of the isotopes. So what we want to do is calculate the percent abundance of this and the percent abundance for this. Now the problem is that when these problems, you don't often know how to start. But what I do know is that I have 2 variables. I have 2 answers I'm trying to find. So we know we're going to apply it to the atomic mass equation. And we know that in order to do that, we need to know what the percentages are, but we're not given the percentages. So here you have to take some creative liberty and say, all right, I don't know what the percent abundance of this is, and I don't know what the percent abundance of this is, but I know I need to find them, and I know that that's 2 separate answers. So I need to make up or use my own 2 variables to represent this. So what I'm going to do is I'm going to represent X to be the percent abundance of this, just the letter X, the capital X, and I'm going to use the letter Y to be the percent abundance of this isotope, for isotope 37. All right? So whatever I get for X, that's going to be related to the percentage for the fractional abundance, and whatever I get for Y is going to be there. Now let's see if we can write this down in a way that makes sense. We are told that the total atomic mass, the average atomic mass, is this. And so that's 35.4527. That goes on the left-hand side of the equal sign because this is the weighted average of all the isotopes. But we know that this mass is at some unknown abundance, and this mass is a different isotope at yet another totally unknown abundance. So even though you don't know how to proceed, go ahead and write down what you know. So what we have is we have 34.9689, and then that's multiplied by X, percent abundance, right? And then we're going to add to that this mass right here, 36.9659, and this is Y, percentage abundant. Would you agree that this equation correctly describes the situation? You have some mass of an isotope multiplied by whatever percent abundance it has, and you have another isotope with whatever percent abundance it has, and once you add these and multiply and add these, it should equal the average atomic mass of chlorine, assuming these are the only 2 isotopes of chlorine, which is what our problem is saying. Now the problem with it is that you have 2 unknowns, and you only have 1 equation. So how do you solve it? You need to have some additional information. And that's when you start racking your brain thinking about, what do I do? What do I do? I don't have enough information to solve this problem, and you start to give up. But then you remember, hang on a second. The problem says that these 2 isotopes are the only naturally occurring isotopes of chlorine. So yes, they are going to be different answers, but what we actually also know is that whatever X is plus whatever Y is, the percent abundance here plus the percent abundance here, it must add up to 1, which means 100%. Because remember, in this equation, whatever we multiply by, it's never the percentage, it's just the decimal equivalent of the percentage, just like we did here. This was 49.31%, but we wrote it with the decimal two places to the left. And this is 50.69%. We wrote it with the decimal 2 places to the left. When you add these percentages together as a decimal, you get 1. 1 is 100%. So whatever this percentage is expressed as a decimal, plus this one has to equal 1. That means that even though x and y are different numbers, and we have two answers, they're related to each other. If you know what x is, you know what y is because they have to add to 1. If you know what y is, then you know what x is because they have to add to 1. So they're not really totally independent numbers. They're linked together because of this, because this is true. So then what you can do is you can solve this as like two equations. This is equation number 1 and this is equation number 2. And so what you're going to do is then you're going to say that y can be equal to, if you solve, subtract x from both sides, 1 minus x. Just subtract x from the left and x from the right, and that's what you get. And then what you're going to do is you're going to take this value of y and you're going to stick it into that place in the equation. This comes straight out of algebra, solving a system of equations with two unknowns. So again, when you're in math class and you're not sure, like, why do I care about solving a system? This is a perfect example of an actual problem where we have two equations and we have to solve for one, stick it into the other. So with all that talking out of the way, what we get over here is 35.4527. And then we have over here 34.9689 multiplied by x. And then over here we have plus 36.9659. But the value of y is really equal to this, 1 minus x. And now we only have one variable, the x variable, and we can solve this equation. Now we have some big numbers, but that's not going to be a big deal. So let's write this again. 35.4527 equals 34.9689 multiplied by x. Here we have to use the distributive property. We multiply in this number times the first term and then times the second term. That's how we solve this equation. We multiply in. So we have plus, this times the 1 is 36.9659 times 1. And then we have a minus sign here, so it's going to be minus, and then this times x. 36.9659 multiplied by x. Make sure you understand, everything is copied from the previous line. We just take this times 1, and then this times negative x, so you have a negative this times x. So now we have to collect like terms. We have an x term here and an x term here, so we're going to combine that. 35.4527 equals, when you take 34.9689 and then you subtract from it a bigger number, 36.9659, both of them are x terms, what you're going to get is negative 1.997x. Then you still have this number left over, plus 36.9659. All we did was we took this term and subtracted away a larger number, so we got a negative number times x. This number just stayed along for the ride. Now the next thing we need to do is take this number and move it to the other side of the equal sign. So when you take this and you subtract 36.9659 on the left, you're going to get a negative 1.5132 on the left, and then you have the negative 1.997x on the right. So then how do you solve for x? You divide by this number in front. So x is equal to this over here, negative 1.5132, divided by this number here, negative 1.997. And so what you get is you have negative divided by negative is positive, and whenever you say 1.5132 divided by 1.997, you get 0.7577. 7577. All right? Now that's the x, the answer to x. How do we find y? Well, we go up here and we know that y is equal to 1 minus x because they have to add up to 100. So since y has got to be equal to 1 minus x, that's equal to 1 minus this number, 0.7, if I can get there, 7577. And so the percent abundance y there, when you subtract those numbers, is 1 minus 0.7577, you get 0.2423. All right? Now, what do we do with this stuff? Well, we go back to our problem. And actually, I think what we can do, yeah, we don't even need to write anything on the next board, actually. what we were saying is that the variable x represents the percent abundance of this isotope. So let's just erase this because that was just a note to ourselves what we were solving for. And what we figured out is that x is equal to 0.7577, but expressed as a percentage, you multiply by 100, 75.77, 75.77% abundance. And then y expressed as a percentage, move the decimal, 24.23. 24.23% abundance. So the answer to the question was, if you read the question exactly, it says calculate the percent abundance of each isotope. Okay? And so what we figured out is the isotope chlorine-35, the lighter of the two isotopes, has this mass that was given to us, and it has a percent abundance of 75.77% in nature. Chlorine-37, which has 2 extra neutrons, with this atomic mass, has a smaller percent abundance, 24.23%. And you can see that these are going to add up to 100% once you add those guys up. So it all makes sense. Now, this is more of an algebra problem, all right? So the easier problems are basically like, here's a bunch of data, calculate the average atomic mass. And then when we go backwards, a lot of times we have to write equations to solve them. But notice the secret of this thing, we didn't have to actually do anything new. Like we didn't introduce a new equation, we used the same thing. The average atomic mass across all isotopes was equal to each individual mass multiplied by their percent abundances. The only secret here is basically inventing a variable for this percent abundance, inventing a different variable for this one, and putting them in there and recognizing that these percent abundances have to add to 1. After you have that, you use algebra to figure out the answers. And so this is why we say math is the language of science. So science, we put forth models, we do experiments, we collect data. Math is what we use to crunch the numbers, to calculate and to solve problems. And so you're going to be expected to draw from your math skills in the past. And so I tried to walk you through it, to kind of refresh your memory if you haven't solved an equation in a while. But you're going to be expected to do that at least some of the time in chemistry. Some of the time we don't use equations too much in chemistry, but oftentimes we do, depending on the problem. And when you get to physics, it's all equations. That's all it is. So I'd like you to go through this again, especially if you don't quite understand the solution. Go through it a couple of times. If you're really having trouble with something like this, it just means that you need a little more practice with algebra. So you would need to back up the truck and maybe go review how to solve equations. So I'd like you to go through this. When you feel like you understand this, follow me on to the next lesson. We're going to dive in a little more detail into understanding the periodic table of the elements in the next lesson. Learn anything at mathandscience.com.